Okay. All right, thank you. So this is joint work with Rui Chao, with Chris Sutherland, and with Tomas again. As we've seen several times, if you have an n-qubit system, it has 2 to the n dimensions. And this exponential, it's really exciting to us theorists because it means that quantum computers can be exponentially powerful. They're really cool. But as experimentalists have been implementing quantum devices, it's turned out to be somewhat problematic because it means that you have this exponentially complex system. And so how can you hope to understand it? How can you hope to test these systems and understand, know what they're doing? And so if you have a really small system, it's not so bad. So if you have 10 to 20 qubits, maybe then you can simulate that on your classical computer efficiently. You can run tomography procedures to see exactly what they're doing. If you have a really large quantum computer with, say, millions of qubits, then you can start factoring some large numbers and just blow up RSA. And then you're happy. You don't even care what it's doing. But in this medium scale that people are starting to approach, when you have more than 20 qubits but less than a million, maybe 50 odd qubits or so, then tests become a bit more complicated. So I think a natural thing that experimentalists are going to be doing more and more is probably to test error correction. Today, I'm going to give a new test, which is how to test the dimension of a quantum system. So before explaining the quantum problem, let me say something about the analogous classical problem. So say you go to Amazon to buy an SD memory card for your camera. This one looks pretty good. It's 64 gigabytes. It's a good deal. Before buying it, you should look at the reviews. And in particular, here's the top review. This is not photoshopped. So apparently, this card that they're selling for a 64 gigabyte card, it actually only has, they say, 10 gigabytes on it. It's a knockoff card. And it's sort of interesting how these things work. So if you plug it into your camera or your computer, the firmware will say it has 64 gigabytes. It'll pretend to have 64 gigabytes, but it doesn't really. And so I don't know exactly what it does. Maybe it's doing something like this. So it's sort of remapping this virtual memory space down to just 8 or 10 gigabytes of actual memory. This is kind of a problem if you take too many pictures, but maybe you won't notice it originally. So fortunately, this is something that you can test. There's programs you can download if you trust them. Fake flash test. And it's also easy to come up with theoretical tests, right? So if you want to check that you have 64 gigabytes of memory space, you can just say, come up with 64 gigabytes of random bits, store them to the card, and then read them back and see that it works. That's a good test. Or if you can also, instead of checking all 64 gigabytes, you could just check a random bit and make sure that one bit is correct. Because the card doesn't know in advance which bit you're going to ask for. It still has to remember all n bits. So that's a classical problem and how you can test it. When you turn to the quantum case, it gets a little bit more complicated because a qubit, a quantum bit, is a continuous system. And so this means that they can just overlap a little bit, for example. So it just basically gives you more ways that the quantum SD memory card can cheat you. And so, for example, here I'm showing a picture. Imagine that you have a 4-dimensional system. So there's actually 2 qubits there. But when you tell the card to access qubit 1, it does that. But when you tell the card to access qubit 2, what it does is it changes basis. It applies a unitary that's close to the identity, but not quite. Then it accesses qubit 2, and then it undoes the change of basis. And so in this way, when you write to qubit 2, you're actually just slightly changing the state of qubit 1. So in this sense, the qubits overlap, which I'll just draw pictorially like this. So our first result says that if you have n qubits and you allow them to overlap, you don't need 2 to the n dimensions. And in fact, you can do this and you can pack them together in just polynomially many dimensions. And technically, the statement says if the overlap is epsilon, then the dimensionality is only needs to be n to the 1 over epsilon squared. And so in other words, this system that appears to be exponentially powerful, it's not so powerful at all, and it actually can be simulated efficiently on a classical computer. Here's the idea of the proof. You can't just throw the qubits down at random. That won't work, but it's not much more complicated than that. So what you do is you just start with Johnson-Lindenstrauss. You throw n vectors down at random into a log n dimensional space, and these vectors will end up being nearly orthogonal to each other. From the vectors, you can convert those into fermions acting on the exterior algebra, which gives you an exponential blowup in the vectors in the dimension. And from each pair of fermions, you can get a qubit. It's sort of a mechanical algebraic construction. It's not so bad, thanks. And just to say it again, my definition of overlap is just the overlap is epsilon. It means that when you modify one qubit arbitrarily, it can change another qubit by most epsilon. And so n to the 1 over epsilon squared dimensions is enough. Here I've plotted n to the 1 over epsilon squared versus the overlap on the x-axis. And you can see that if epsilon is more than about root log n over root n, the dimension is less than 2 to the n. So if epsilon is sufficiently large, you get an improvement. On the other hand, if epsilon equals 0, if they don't overlap at all, then you really do need 2 to the n dimensions. They're in tensor product. So we also have a small result that says you can pull apart qubits that slightly overlap. And so if the overlap is up to 1 over n, then you can pull them apart, and it still needs dimension 2 to the n to back them together. And so there's this region in the middle between about 1 over n and 1 over square root of n, where we don't actually know what happens. It's somewhat more complicated, maybe, whether you need 2 to the n dimensions or whether you can do it a bit better. OK, so that's the situation for packing qubits. Let me come back to the question of how do you test the dimensionality of a system. Here again, it's the classical test. You store n random bits, and then you check just one of them, maybe, to see that it's right. Our quantum test is exactly the same, except we store random qubits. So you store n random qubits into your system. Each one is either 0, 1, plus or minus. Then you just check one of them and measure it, make sure it's correct. And so our second theorem says that if you pass this test with probably at least 1 minus delta, say, then the dimension of the system has to be at least 2 to the n times a factor that's like 1 minus n squared delta. So if delta is like 1 over n squared, this gives you an interesting result. It shows that you do have an exponentially large system. OK. So what can you do with this? I think there's certainly lots of open questions. I think it would be interesting to implement this experimentally, perhaps. It would also be interesting to try to, instead of just testing the dimensionality of your system, to try to test the functionality of your system. And this is actually, it's known how to test the functionality of quantum systems, provided you have 2 or more entangled devices. Then prior work has shown how to do this. But giving functionality tests with one device is a lot harder, and that's not known at all. And conversely, I suppose, experimentally, getting 2 separated devices is much harder to implement than just one device. So I think the record for 2 devices is just to have 1 qubit in each device entangled. A final possible application is maybe these kinds of packing results can actually be used for simulating certain kinds of systems in polynomially many dimensions. I don't know. That's crazy. All right. Thank you.
Questions for Ben? Yes, if you think of the physical implementation of the qubits or like on a grid or something like that, then you could potentially imagine that the overlap is higher with your distributed neighborhood and then it just drops somehow. So you don't have a constant overlap with every pair. Do you think that in this case you can still get some...
I don't know. I mean, right, so if you have, say, a lattice, and the overlap drops off really quickly. Like if you overlap only on adjacent neighbors and then it's 0, then it's sort of like it's 2 colorable or something. So you have at least dimension 2 to the n over 2. If it drops off maybe exponentially or something, I don't know, that's an interesting question. I'm not sure though.
In your talk, you gave a randomized construction of packing. Thought at all about explicit constructions? That
I haven't thought about it. Yeah, it's something we do.
In light of the previous talk about areas, suppose you had a Hamiltonian with n terms. Would it be possible for you to find n operators that were sort of very close to them in some way, but that acted only on a much smaller dimensional space, and then try to diagonalize the sum of that in some other approximate algorithm?
I don't know. I mean, that would be interesting. I think sort of like just getting like the right definitions or the right operations or things when you're trying to work with 2 qubits at a time instead of 1 qubit at a time, that starts to get some problems already. So, but maybe it might be solvable. Well, I mean, when you have 2 qubits at a time and they overlap, it's not clear what it means to do like a C0 gate between 2 overlapping qubits. Or you see what I mean? Or to define a Hamiltonian term on 2 overlapping qubits.
Decompose it as a sum of Hamiltonians.
I see. So for C0 gate, it would have to be unitary, and that it wouldn't work. But for Hamiltonian, it might work because you don't need it to be unitary, for example. Maybe, yeah. I haven't thought about it, but yeah, it could be interesting.
Let's thank Ben again.